Okay, so we were discussing the jet flow equations for non-reacting constant density jet. So these are the three equations we need to solve, subject to, of course, boundary conditions. So let's look at the boundary conditions. So you have, okay, so you can see that you need one boundary condition in terms of x, and then two boundary conditions in terms of r. Second order, there are second order terms in the radial direction. Okay. So at the center line, okay, along the x-axis, you have radial velocity 0 at the center line. Then the radial, okay, derivatives, so dvx dr is 0 and dyf dr is 0. Okay. So those are the standard boundary conditions at at r equal to 0. Okay, so that's one boundary with respect to r. The other boundary is r infinity, okay, outside the jet. So at r infinity, okay, Vx is 0 and Yf is 0. Okay. So that's pretty obvious. Any questions? Okay. And then x equal to 0, you have the boundary condition with respect to x. So at x equal to 0, okay, so we assume that the axial velocity and yf, they are uniform. Okay, so Vx is equal to V from r 0 to capital R. Okay. Same way V this is Vr actually, which is 0, and then Yf from r 0 to capital R is equal to Yfe. Typical value is 1, but you can have dilution with nitrogen and other diluents, then it could be less than 1. Okay. And then outside for r greater than capital R, it is 0. This is at x equal to 0. Okay. So these are the boundary conditions. And as we discussed, okay, so the solution will be identical, because here you have nu and here we have d. Okay, they are equal, then these equations are identical, and the boundary conditions are also identical. Okay. Here we have made one more assumption, the constant properties. So nu comes outside. Okay. Similarly, the d comes out, so the differential. So now we'll discuss the solution. So for the solution, I'll just give you background. We are not going to do the derivations. So this is based on a similarity solution assumption, that these equations have a similarity solution. So what does this mean? That there is a similarity variable psi, which is a function of x and r. Okay. So using that function, whatever that function is, so this is a typical boundary layer flow analysis. Okay. In fluid mechanics course, you might have done boundary layer over a flat plate. Okay. So this is very similar, except it's axisymmetric geometry. Flat plate, boundary layer, it is Cartesian geometry, x and y. Okay. So the main idea is, okay, you identify a variable which is a function of r and x, and then you do the transformation of the governing equations. So this becomes your independent variable, and then the partial differential equations they are converted to ordinary differential equation, because they are only functions of psi. Okay. So then there is the analytical solution for the ordinary differential equation. Okay. So there are some derivation involved. Okay, you can find that in the fluid mechanics book. It's not in these combustion books, for the solution. So first of all, what is this? Let me write this, the similarity variable as a function of x and r. So this is rho e times j e. Okay, this will of course rho e j e (16 pi) 1 over half 1 over mu r times x. Okay. So basically, this variable is r over x. Okay. The other things are constant. They are They are included for convenience. They make the equation look a little simpler. Okay. But they are not essential for the analysis. Okay. So what is J E? First of all, what is rho E? Okay. So that's the fuel density, or the density is constant anyway. So this is just one density. Okay. But it's the fuel density here. J E is the momentum flow rate, which is also a constant. So at x equal to 0, so you have the uniform velocity, right, Vx, which is Ve. Okay. So the momentum flow rate will be the mass flow rate. So that's the mass flow rate. I should say rho E. Okay. And the momentum flow rate then will be times V. So that's a constant. Okay. So that's the similarity variable. And then you write the equation with this as the independent variable. Okay, so you'll have the species equation and the momentum equation. And the solution is given by these equations here. Okay, so this is the solution. So let me show the solution from the book. So let's focus on the solution for Vx, and the same solution then applies to Yf. Okay, when the Schmidt number is 1. Okay. So Vx as a function of r and x then is 3 over 8 pi 8 pi j e mu of times x So this is the solution comes from the similarity variable analysis, similarity flow analysis. Okay. And psi is already defined here. Okay. So remember, the psi contains both r and x. So basically here psi gives the dependence on the radius, because you don't see any radial dependence otherwise. Okay. So now if you substitute for J E here, okay, then you can get the solution, which should be on the next page. So that is the J E and psi, and then you substitute for the J E here, then you can get this solution, Vx over Ve. So let's do 1 or 2 steps. So it's 3 over 8 pi. J E is pi r square rho E Ve square mu over x, and then this term, right? Okay, so now you can see this pi cancels, and I can bring this 1 Ve So make this non-dimensional. Okay. So what is left? 3 over 8 rho e v e r mu. Okay. Then there's one more r. Let me make sure. Yeah, r x, and then this term. Okay. Now we can recognize what is, okay, this ratio. That's the Reynolds number. So Reynolds number appears explicitly then. Okay. So from here, so now this is a function of r and x. We can get the axial velocity along the center line. Okay. So along r equal to 0, so Vx0 over V. So earlier we were just plotting it qualitatively, how it varies. Okay. So this gives the explicit variation. So all we do is, when r is 0, the psi is 0. Okay. So this will be 0. So this term will become 1 along the center line. Okay. So this will be 3 or 8. This is the Reynolds number times r over x. So according to this solution, the axial velocity at the center line decreases as 1 over x. Okay. Now obviously this solution is not valid near x equal to 0. Okay. First of all, this is 1 over. Okay. So if x is very small, this is not valid, because for very small x, this will become greater than v, which is okay, which is not possible. Okay. So this solution is valid when r over x, rej 3 over 8 is less than 1. That gives the, okay, x has to be greater than that value. Okay. So for the initial length, it is not valid. Okay. So this puts a condition for the solution in terms of x. But anyway, we are only worried about for large values of x. Okay. So we can use this solution. Okay. So this gives the value along the center line. So first of all, we'll discuss a couple of properties. One is the spreading radius. So I think I can now, if I need, I will use it, but let's use this space. So this jet is spreading like this. So if you plot the velocity here, it's like this. So how do you define this jet radius or the spreading radius? So we define it by saying that Vx over Vx0 is 1/2. Okay. So this is clear. So this is the Vx value, where Vx becomes Vx, this ratio becomes 1/2. We define the spreading radius. Okay. So we call then that r there equal to r 1/2. Okay. So this is a convention you can define by 90% value. Okay. That is, because eventually what is the value of Vx? Far away from is 0, right? So you can do 1/2, or you can use like 0.1, 0.2. Okay. So the answer will be kind of similar. The value will change slightly, okay, if we define by a different ratio. So here we are, this is the standard convention. So to find this r 1/2, all we need is take the Vx divided by Vx0, okay, and that ratio is 1/2. So that will give us the value of small r for the spreading radius. Okay. So, take this ratio, so Vx divided by Vx0. Okay. Move this away, the sound making machine. So, Vx over Vx0, so Reynolds number will cancel out, Rx will cancel out. So, what you are left with is this quantity 1 plus. Okay. So, this is just 1 plus psi square over 4 to the power minus 2. So, that actually gives the velocity distribution as a function of r. Okay. At any. So, now, so this is equal to 1/2, okay, and then you can write the solution in terms of psi. Okay. And so, if you do this, you can check this, you get psi square equal to, I think this is correct, but you can check. Okay. And then what was psi? So, I write the psi square 3 rho e j e. So, substitute for psi square. So, this is now r 1/2 over x. So, this is equal to this value. And now substitute for J e, which is the total momentum flow rate. So, after doing this substitution, you should get this result. This, of course, this is given in the book. R 1/2 divided by x. This is equal to REJ times 2.97. So, let me double check the solution. Yeah, so that's the solution for the spreading radius. Okay. So, this also defines the spreading angle. I don't know if it is plotted anywhere. Yeah. Okay. So, this is like showing the jet coming out from a very small radius. So, this spreading angle, because this is r 1/2 and this is x. So, spreading angle is simply tan alpha, which is r 1/2 over x. Okay, so, that gives the, based on that, the velocity drops to 50% of the center line value. Okay. You can also define using YF becomes half of center line value. Okay. So, anyway, for us more important is the YF distribution. So, let us focus on the YF. So, from first of all, what is the YF at the center line? Okay. YF at the center line has the same solution, like, so divide by YF, which is 1 at the, okay, at the jet boundary. This is the velocity, so this is 1. Okay, because at the jet boundary YF value is 1. Okay. So, this gives the value along the center line of the jet. Okay. So, that will be 3 over 8 REJ r over x. Okay, now let's substitute for Rej. So 3/8. So it's rho e v e r. Okay. So what's in the denominator? We're substituting for the Reynolds number. Mu, which is will be rho e times d, because Schmidt number is 1. Okay. And then r over x. Okay. So YFO 3/8. So rho e cancels. VE over r. This becomes r square 1 over x. Okay. So if I, okay, so let's keep it like this first of, okay. So now you see this, the YF at the center line is decreasing, okay, 1 over x. Okay. So to find the flame length, YFO should be equal to YFS, and then the x will give us the flame length. Okay. So if you do that, then the flame length will be 3/8 V r square over d divided by YFS. Okay. So this is the utility of advantage of, or the benefit of this non-reacting jet, constant density jet solution. Okay. It gives us the distribution of YF, which may not be totally realistic, but it gives the qualitative distribution. Okay. That is, YF value is decreasing along the center line. In this particular case, it decreases as 1 over x. And from there, we can extract the flame length. So if you remember the solution we had earlier from the scale analysis, okay. So look at that solution. So from scale analysis, we had LF as VE r square, okay, over d, right? So those three variables are here. Those are three parameters are here also, V r square d. In addition, now we get, okay. Of course, this again gives you qualitative picture. It won't give you exact values of LF, but it gives the correct variation with these four parameters. Okay. So this gives you also, the variation with fuel air ratio. Okay. For different fuels, YF value is different. Okay. For example, now if you take, let's say methane, what is the value of YFS? So CH4, no, I think it's like 0.05. 17% you are saying?
Air-fuel ratio.
Oh yeah, air-fuel ratio is correct. Yeah. So if you look at this fuel and air for stoichiometric condition, okay, then YFS so mass of fuel is 16 and mass of air is 4.76, nitrogen or air is 28.9. So I think this is about 0.05, maybe 0.055. We can check later. Okay. But if you take hydrogen, this value is smaller. Okay. So now for hydrogen, this is 2. Oh, wait a minute, this is not correct, right? This is YF. So we have to add here 16 also. It's the mass fraction of fuel. Okay. So this will be 2 plus mass of air is, I think, 1.88. So for hydrogen it is H2 plus 1/2. So no, 2.88, right? No, 2.38. So you can check this. Times the molecular weight of air, which is 28.9. So 2 divided by 2 plus, okay. So what is this value? Let's calculate this quickly. I don't have, remember this. So this is 2 divided by 2.38. Times 28.9. Sorry? So this is 0.0242. Let's see. 28. Oh, yeah, 28. Okay, 028. So if you use this value, okay, for hydrogen, that will increase the flame length. Okay. But there is also another effect, the diffusivity. That will diffusivity is much higher from diffusion for hydrogen, so that will decrease the flame length. So anyway, there is the effect of fuel through YFS. Okay. So that gives the flame length. We can also get flame shape from the solution. So for our flame shape, we look at the solution for YF. I have to rewrite that one. So that's 3/8 pi So we had written it before. I will write the final solution. QF over D 1 over X psi over 4. So now if you look at qualitatively the distribution of YF in this flame, I need a different color. So this flame is given by the YFS locus. So the flame surface is located along the loci of YFS value, YF equal to YFS. Okay. So if you plot the contours of YF, because this equation gives us the contours of YF. Okay. Because all you do is take any value of YF, let's say 0.9. Then this equation QF is constant, diffusivity. This gives you an equation between R and X. So if you plot R versus X, okay. So if YF is say 0.9, so it will give us that contour. So this will be like 0.9. Okay. You take another value for YF 0.6, it will give you another contour. Okay. So you can get different contours of YF, okay, by just picking whatever values you want. Okay. So then YF equal to YFS, that gives us the flame shape. Okay. So the contour corresponding to YFS gives us the flame shape. Okay. So substitute this equal to YFS, and then you can plot, you can even make a Excel sheet. And from Excel sheet you can get R as a function of X. Because remember the psi is just function of R and X. Sorry? Oh yeah, minus 2 here. Thank you. Okay. So you can write this in a different way. You can write this as 1 plus psi square over 4 equals to 3 over 8 pi (1 over x). And then you can take 1 on the other side, take the square root. So then you have a direct equation for R, okay, in terms of x. Okay. Okay, here also we had to discuss this a very interesting approximation called the flame sheet approximation. Okay. So we are assuming that fuel and oxygen, they come to this flame and the combustion occurs instantaneously. Okay. So in the limit, that means Dam-Kohler number is 0 or Dam-Kohler number is infinity. Okay. So the reaction time is 0 compared to the diffusion time. Okay. So that's the flame sheet approximation, that the Dam-Kohler number is infinity. Okay. And the transport times are much larger than the reaction time. Reaction time is 0 in the limit. So if the reaction time is 0, you can imagine that the flame, okay, it becomes a surface. The reactions are only occurring at a surface, not in a volume. Okay. So the real case, of course, let me first show the solution, then we'll go back to the PowerPoint. So we discussed all of this. There is an example here, but okay. So the locus of points where the equivalence ratio equals unity. Okay. We are using YFS, which is same thing. Okay. So that gives the flame surface. So these shows some contours in terms of phi. We were doing this in terms of YF. Okay. So at the flame surface, phi is 1, which is YF equal to YFS. So if you're going to refer to this book. Yeah.
How do you classify this diffusion flame as laminar and turbulent? Is it on the basis of the tube Reynolds number or jet Reynolds number?
They are same, right? What do you mean?
In the jet Reynolds number, we use rho v r by mu. Whereas for tube, we use rho v d by mu.
Oh, yeah, I think it's
Is the classification based on the jet Reynolds number or tube Reynolds?
okay. Okay, no, I understand what you're saying.
Classification as laminar or turbulent.
Yeah, I think normally you use the jet Reynolds number. Okay. Of course, it's not a fixed value first of all. Okay. But we have done a lot of computations. Yeah, if you exceed like about 1,000, 1,200, okay, then you get into fluctuations in the flow. You don't get stable flame, laminar flame. Okay. When you do DNS. Okay. Yeah, good question. So yeah, it's all based on here, jet Reynolds number. Okay.
But that depends on which parameter the observation where turbulence property is started.
Yeah, turbulence, the transition Reynolds number is not fixed. It depends on your flow conditions, how smooth you can make the flow conditions. If you make your flow very smooth, then you can go close to 2000 or even higher. Okay. So if you are going to study from this book, read this stuff, then they are using phi. We were just using directly YF. And this is what we discussed and derived today. Flame length. Okay, now in the textbooks, okay, a lot of people discuss this Burke-Schumann flame. How many are familiar with the Burke-Schumann flame? Okay. Sorry? Yeah, Burke-Schumann. So Burke-Schumann, these were two engineers who derived a solution for this axisymmetric, reacting jet. Okay. So basically, they use the same equations we are discussing today, okay, for axisymmetric jet flow. But they made very crude assumptions, I shouldn't say crude, very drastic assumptions. Objective was to get the solution for YF. Okay. So I'll just show you quickly. So a lot of assumptions are same, which we already discussed. Like flow is laminar, steady, okay, so on, 3 species, and the flame sheet approximation, which means the Damkohler number is infinity. Okay, species transport given by the all those assumptions. Then another drastic assumption they made was here. I think I'll skip all of this. Let me just focus on the Burke-Schumann. Okay, page 352. Yeah, it's further down. Oh, Burke-Schumann, okay. So different books had little different treatment for the Burke-Schumann. Okay. But they were interested in solving this equation. Okay. So they made a drastic assumption that the Vx is constant. So they don't have to worry about solving the momentum equation. Okay. Which of course is a very drastic assumption. Vx, you remember in the flame, how much Vx change? How much does it change? It can increase by a factor of 7. Okay. But anyway, using that assumption, they get the solution for the flame surface. So this is the equation they are solving. Now Vx is a constant. Okay. So this equation now has an analytical solution. Okay. I think you teach heat transfer, you probably have seen similar equation for temperature. Okay. So there is a well-known analytical solution which comes in terms of Bessel functions. In heat transfer also we do that when you have temperature varying in the axial direction and in the radial direction. Okay. And you get the solution in terms of this Bessel functions. Okay. So I will not go through this, but this is also a solution which is discussed in the classrooms when you study this. And this was done, this was reported I think in like 1920s, 1928 or 29. Okay. So this is not like very, very old, yeah, it's old. Okay. And then, since then, many people have analyzed these diffusion flames. They are computed, numerically, and they always try to compare with the Box-Schumann flame. Okay. So this has been like one of the classical solutions for jet flames. And then there are some other solutions. We already discussed the constant density solution. Then here there is a reference to Fay. Okay. So they solve the variable density. Okay. They got the variable density jet solution. Okay. So if using that, okay, you get a different solution for the flame length, but the basic parameters are still there. Okay. So what are the basic parameters? We can identify YF stoichiometric. Okay. MF dot now is QF times rho E. Okay. So it's the same. So there's another rho now, ratio of the ambient density, and this is some reference density. Okay. And this is the density of the fuel. Okay. So there's some density effect appears in this solution. So then you can write the same solution in a more familiar form. So here you have the diffusivity, YF stoichiometry, and QF. Okay. Then there are some factors which are, dependent on the densities. Okay. So this is the extra factor, you can say. And now, of course, there are now a lot of numerical solutions for this jet flame. Okay. So you solve the full equations for the axisymmetric flow. So you solve all the equations. Okay, continuity, species now you can have depending upon your reaction mechanism. Okay, large number of species, and then the energy equation. Okay, and I showed you some solution yesterday. Okay, so I'll show a couple of other solutions later on. But there are lots of solutions. So here they mention about maybe 3 or 4 different solutions, numerical solutions. Okay, so now we can go back to the PowerPoint. So this part we already discussed. Okay, any questions? So we discussed this part already. The rest of the material we are going to discuss, more on the flame length. Okay. So after lunch, I'm going to discuss some solutions, especially for solutions for the flame length, and then how does this flame length vary with other parameters. Okay. Some are already there, like V, R, YFS, D, and then there are few more.